Hey, physics students. Going to do this Waves Unit 1, Worksheet 1 and Worksheet 1B. For us, this is our Unit 10. Called something slightly different on here, but no matter. They're pretty similar. I would recommend, if you had any trouble with either one or some things didn't go exactly right, try the first one, go through the first one with the video here, and then return to the second one and try to fix it up yourself before you watch the video. That would be good practice, I think. Alright, so let's see what we got here. Diagram to the right, so this is the classic mass on spring situation. Attached to a Hookean spring, that just means that it's sometimes we say it's a linear spring, sometimes we say it follows Hooke's law, sometimes it's called an ideal spring. It just means that all the things that we think are true about springs are true for this spring. That's what that means. It's on a frictionless surface, so that's all good news. Block experiences no net force when it's at position B, so that means this is like the equilibrium position. The spring is neither stretched nor compressed at that position. When the block is to the left of point B, the spring pushes it to the right. When the block's to the right of point B, it pulls it to the left. Well, duh, we knew that. It's a restoring force. The mass is pulled to the left from point B to point A and then released. So it's going to start at point A. The block then oscillates between positions A and C. Consider point B to be 0 position and to the right of B to be positive. So that all jives with what we would have done anyway. On the grid below, sketch the graph that you think reflects how the restoring force applied to the block by the string changes as a function of time. All right. So we're going to make all these graphs, force, acceleration, position, and velocity. I don't know that I would necessarily make them in this order. I think that it probably makes sense to me anyway to start with the position time graph. So it's starting at position B, right? And then we're going to go, wait, hold on a second. After considerable yes, it's starting at position B. And well, I guess I feel like this doesn't quite, the way that this is laid out with these letters, it doesn't quite match up. Because if we're saying here that we're starting at position B, I feel like it should be starting at position A, because that's where they're going to compress it to there and let go. But anyway, I'm going to go with what it says here. So in other words, I'm going to start keeping track when it's at position B headed toward position C. So position C is like the positive max, and A is like that negative maximum displacement. So when it's back to B again, position is there. So you can see what I'm doing there. It's starting at position B. That's when it's at position 0. And then going to go to C, and then back to B, and then to A, and so on. So as we map that out over time, it's going to look like this. I'll go ahead and do, is that 3 cycles? And of course it would continue. I should tell you what the secret is to drawing really nice looking sine and cosine curves, because come on, that's beautiful, right? I mean, look at that. It's a thing to behold, mathematical, beautiful object. Okay, so what do we want to do next? I guess we could do the force next. When the spring is at position 0, at position B, there is no force, because force is equal to kx, and there's no force there. So at all the B positions, there's no force, because the spring is neither stretched nor compressed. Okay? Now, when it goes to position C, that's when the spring is pulling back on the object this way. And notice I'm pointing toward the negative, right? So when I'm at position C, the spring force is pulling back in the negative direction. So that's going to be negative there. And then position A, it's going to push it that way. They said as much in here, but we could have figured that out without them telling us that. Okay? So here's the trick to drawing really beautiful sine and cosine curves. It's got to be flat as it goes through here. Like a really terrible cosine curve or sine curve is when you have the dots and then you like connect them like this, because it's not like that. It's not pointy. So what you're going to do is when you come through this point, you're going to aim like you're headed toward this point but going to miss it to this side. And like I'm aiming this way, and then you make your nice curve through and keep curving through. And now I'm going to curve up onto a line that's going to miss this one off to this side, which gives me a chance to come back through here. And then going to miss off to this side, and then going to miss, and then going to miss, and so on. There's the secret. You could be a math teacher now. You might notice here that the position graph and the force graph are exactly upside down of each other. The scaling on these axes, the vertical axes, would be different, but the shape exactly upside down of each other. Someday when you take calculus, there's relationships that you will understand better about all this. Now, acceleration, unbalanced force is equal to mass times acceleration. So that means the force and the acceleration graphs are going to look exactly the same, because force equals mass times acceleration. So whatever the force graph is divided by mass, and you've got the same thing, and you're dividing by the same number, right? So it's going to be the same. Same. And the velocity graph, the way I like to think about this one is as it goes through here, as it goes back and forth, when it's at A and C, that's when the velocity is going to be 0, because it's going to be turning around, right? So at all of the A and C points, those extremes, those are the turnaround points. That's where we have to have a velocity of 0. At position B, it's headed toward position C, right? So it's got positive velocity. Sorry, when it's at position C, let's go from here. When it's at C, headed toward B, it's going to go in the negative direction, right? This is going from C to B is negative. And then from B to A is also negative. So these are all negative velocities that make this bump like that, where the maximum velocity happens at B. And then from A to C, that's our positive velocities. And then from C back to A, and then from A to C, and then from C to A, and then from A, and so on. So that's going to look like that. You could also think about the slopes of this. Velocity is the slope of position. So here, like that would be my biggest positive slope there. Here, slope is 0. Here, slope is biggest negative. Here, slope is 0. Here, slope is biggest positive, and so on. So that works too. All right, so if you had any kind of struggles with that, then go ahead and pause this and see if you can fix up your worksheet 1B. Obviously, like I do when we have a test on this, which we will in a couple weeks, I'm not just looking for, I'm like, oh yeah, this one looks like that, and this one's kind of like that. Like I'm looking at the detail about where those maximums and minimums are lining up, right? It's not just a matter of making some squiggles. I know that's kind of what it looks like, but the details are important where the maximums and minimums are. All right, let's do it again. Same deal, except this one's going up and down. So The diagram to the right shows the block. The block hangs at rest at position B, so this is the place where the gravity and the spring force will be equal to each other. All right. Sketch a force diagram for the block at positions A, B, C, B, and A as it moves. So the spring, I think at position A, we could imagine that that's where this spring isn't stretched anymore, so there's no upward spring force. You just have the force of gravity. And then at B, that's where they're equal. And then at C, when it's all the way down here, if you're all the way down there, then spring is stretched more. And so on. Oh, got to do this one again. Right? It would look like that. They told us here that this is a spring that is only stretched, not compressed. So we never have a spring force pushing down, just pulling up. Okay. On the grid below, sketch the graph that you think reflects the net force acting on the block as it changes as a function of time. So similar exercise. We can go ahead and do that one first. So at position A, right here, the net force is going to be down, so negative. And then at position B, forces are balanced. And at position C, the spring force is going to be winning in the up direction. And yada, 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 yada. Like that. Right?
Teachers, please excuse this interruption. At this time, would the current 9th grade, 10th
acceleration
grade, 11th grade players that play JV or varsity volleyball please meet in room A3? That's any JV or varsity volleyball player from 9th, 10th, and 11th grade, please meet in room A3.
I'm sure glad I don't have any of those volleyball players or have a class right now, because if they did a surprise move like that, I'd be pretty mad. But as it happens, don't have a class right now. So acceleration and net force are the same. I did 2 full cycles this time. And position, when we're at position A, that's maximum position. So if we take up to be the positive direction, position B is in the middle, and then position C is down there. So like that. And just like with the one we did on the last page, it's perfectly upside down of those. And then the velocity, well, the velocity is, if I think about slope, at the velocity, here's all the places where the slope is 0. So 0, 0, 0, 0, 0. Here it's going in the negative direction. These are all my positive slopes. Negative and positive. Oh, there you go. That's how you make those graphs. Am I going to make you do that on the test? You betcha.